Okay, so we're going to talk about the polynomial Euclidean algorithm now, and you'll notice that it's basically exactly the same as the Euclidean algorithm for z, and it's exactly the same because the Euclidean algorithm for z just used the division algorithm repeatedly. So what are we going to do? We're going to use the division algorithm repeatedly, only instead of our elements being integers, they're going to be polynomials. That's okay. So let's get started. So f is a field, and f and g are an f of x, f adjoint x, not both 0. Not both 0 because if they're both 0, then the GCD doesn't exist. But as long as they're not both 0, we're okay. To compute the greatest common divisor of them, we're going to construct a sequence of remainders, as we did with the regular one, with the integers rather, not the regular one, where we're going to set r negative 2 to be f without loss of generality. F is the one of the bigger degree when you set this up. R negative 1 to be g, and we're going to initialize I to 0. And then what we're going to do is we're going to use the polynomial division algorithm, which I'll call PDA, to divide. All right, right now I is 0, so I'm going to write Ri minus 2 by Ri minus 1. So what we're doing here, since I is 0, is we're dividing R negative 2 by R negative 1. That is, we're dividing f by g. And when we do that, what we get is some quotient and then some remainder. And I'll call the quotient qi and the remainder ri. The quotient's not very important for what we are going to do, but I'm going to index it anyways. And then we're going to ask if the remainder is 0. So if ri is 0, stop. The GCD of f and g is the previous step. Okay, so if I is equal to 0, it's saying in this case, if Ri is 0, the remainder is not there. So Ri minus 1 goes in. Oh, shoot, I missed my I here. There we go. Ri minus 1 goes into Ri minus 2. In particular, R negative 1 goes into negative 2. So G is already a factor. So we would stop there. Otherwise, you get some remainder. And so what do? Well, you increment I by 1. And repeat. That is, you divide, just to write it out, you're going to divide Ri minus 1 by Ri. So you go up to the next level. So let me just talk about why this terminates and why this works. And in the next video, we will do a couple of examples. So when you do this, what you're going to get, so the polynomial Euclidean algorithm produces this sequence as follows. Let me start off at 0 rather. So R negative 2 is some Q0 R negative 1 plus R0. And then you divide R0 into R negative 1 to get some quotient. And then some other remainder R1. And then you divide R1 into R0 to get some other quotient. And some other remainder R2. And you keep going. And you keep going. And you keep going. And eventually what you're going to get is that when you divide Rn minus 2 by, I'll turn it into a heart, by Rn minus 1 with remainder Rn, when you do the next step, what you're going to find, let's suppose here that Rn is not 0, you're going to find at some point when you do the next step, you get 0. So that is Rn plus 1 is 0. All right. So the GCD of Rn is of f and g is right here. It's this Rn. Okay. Now let me tell you why this is going to stop. So here you start with f and g. When you do the division algorithm once, at this step, the degree of R0 is less than the degree of G. In particular, the degree decreases. At this step, the degree of R1 is less than the degree of R0, which is less than the degree of G. So at each step, the degree goes down. Well, there's only finitely many times that we can go down before we're either a constant or we're negative, or it goes in evenly and we get negative infinity. So this will terminate because the degree decreases at each step. And a process is called an iteration. So every iteration it decreases. So that's why it decreases. And then in the next video, we're going to do some examples.